Right, good afternoon, guys. Um, so today we're going to be discussing confidence intervals, and I know we're meeting in a different circumstances, under different circumstances where I can't see you and you can't see me. But I hope you guys are safe and are keeping yourself safe and distant from others during this time of the COVID-19. And uh, just remember to take precautions when going out and just stay safe. And so bringing to you this lesson, because I know it's kind of difficult to look at a PowerPoint and understand what's going on. So I just wanted to give you kind of a video of me explaining what I want you to get from the PowerPoint. And today we're going to be talking about confidence intervals, and I would highly advise, if you watch the video that I put on Blackboard before watching this video, it kind of makes more sense of what the purpose of confidence intervals are. And I'm going to try and give you guys some examples as to what they're used for, what's the importance of them in statistics. And so to start off with the definition of what it is, right? Confidence interval is something that's constructed so that the value of the characteristic will be found inside the interval. So what that means is, what we learned from the previous lesson is that a lot of our research, we deal with collecting samples. And with those samples that we collect, we try and predict what the true parameter will be. For example, in the Rhesus experiment, right, we collected different samples of Rhesus pieces, and we were looking to see if our data showed that 50% of the Rhesus pieces were orange, right? And the goal of confidence intervals is to kind of estimate, how far are we from the actual true parameter? Okay, and so each of us obtains a sample, and that sample is our estimate. And the confidence interval, the interval that we can confidently say that we have the parameter in, is determined by the margin of error. So our sample estimate, that's what we collect, that's what we sampled, plus or minus the margin of error will determine how large of an interval we have. Okay? And then questions would be, what factors into a margin of error? Well, this plus or minus, remember when we looked at the normal line actually, the confidence interval is an estimate plus or minus the margin of error, right? The confidence interval is equal to an estimate plus or minus the margin of error. So keep that in mind. Okay, I'm going to go back. Model. We would go plus or minus 1 standard deviation above, or plus or minus 2 standard deviations, and we had the empirical rule that had these percentages. So in the margin of error, what we're factoring is, if I have a sample estimate and I want to have 68% confidence interval or 95% confidence interval, that's just determining how many standard deviations away from my sample data I want to go to. Okay, so that's kind of a textbook explanation. One interesting fact that I want to mention is, interestingly enough, in history, there's shown different statisticians that use this method of confidence intervals. Specifically in World War II, if any of you are interested in your history classes on World War II, there was this incident called the German tank problem. And if you've heard of it, awesome. If not, you're going to hear about it today. But the German tank problem took place in World War II. And I'm going to scroll down to the actual story. And the issue was, there was the Allied power and the Axis power. And the Allies wanted to know, or estimate how many tanks the Axis powers had. Because they had heard rumors, and so let me show you where it says that. Shortly before D-Day, there was rumors that indicated that there was a large number of tanks being used by the Axis powers. And so the Allies wanted to determine if this was true. So they wanted to estimate the number of tanks produced. And what they ended up doing is they would look at the serial numbers of captured and destroyed tanks and use those serial numbers to kind of get an idea of how many tanks there were. But those serial numbers, the captured tanks, the destroyed tanks were their sample. Okay, they were trying to figure out exactly how many tanks the Germans had. So they used statistical methods, and let me zoom in here. Let me see what it says. Where did I see it? Yes, it's actually down here. Okay. So it says specific data. According to the conventional Allied intelligence estimates, the Germans were producing around 1,400 tanks a month between June 1940 and September 1942. Applying the formula below with the captured tanks, the sample, right? The number was calculated to be 246 a month. After the war, the German production figures were captured, and they found out that in actuality, the number of tanks produced per month was 245. So the Allies estimated, using statistics, using confidence intervals, they estimated that the Germans were producing about 246 tanks a month. In actuality, they were producing 245. So that's a pretty good estimate, if you look at it that way. And then here we have, their statistical estimate for a given month, and the actual German records. In June, they overestimated. June 1940 they overestimated. June 1941 they were pretty close, but they underestimated. And in August 1942 they underestimated. But these were pretty close compared to the intelligence estimate, right? So what they used here, the principle that they used here, was confidence intervals. Okay. And so, a little joke here, right? This is a Garfield comic strip, and it says, Garfield is looking at the weather, and it says, taking a look at tomorrow's weather, the high temperature will be between 40 below zero and 200 above. And then Garfield turns to the audience and says, this guy's never wrong. Right? And so this just shows, you can say that the true estimate is between an exceedingly large lower bound and exceedingly upper bound, but that doesn't show precision, right? It just shows, you're throwing a large interval and hoping that you're going to be right. But what we're looking for is not only, a large enough interval, but we're looking for precision and accuracy. Okay, so the next thing I want to look at or tell you about the slides is the formula, right? The formula for the confidence interval. How do we determine it? And so to determine this confidence interval, we're trying to estimate the parameter. Remember, X bar means the sample data. So if I collect data from a sample of people or a sample of objects, and I take the average of that, that's my X bar. And then plus or minus the margin of error. The margin of error is dependent on the standard deviation for the mean, which we've seen this formula before when we talked about sampling distribution. And a little extra thing is you have to multiply the standard deviation by the z-value, and the z-value is dependent on the confidence level. If they say 90%, 95%. So one thing I want to mention here, and I'll write it out for you guys, is this z-value is dependent on the confidence level, which is the percentage. Okay. And what we learned how to do it in the normal table is we would take a given percentage, look for it in the table, and find the corresponding z-value. Okay. The confidence level associated with an interval is the approximate success rate of the method used to construct the interval. Okay, so if you choose a 90% interval, a 95% interval, the larger your percentage, the larger your interval. The smaller your percentage, the smaller the interval. But it's like if you're catching a bunch of fish. If you throw a large net, you're bound to catch more than if you threw a small net, right? But again, if you throw a large net, you're kind of broadening your scope, and so the precision is not there, but you're widening your net. Okay. Let's see. All right. So a couple of things is in the AP exam, they're going to ask us to kind of make sure that we talk about certain points. And so in this next slide, on step I, what we're going to do is construct the interval, find the interval. Okay. An overview of the procedure that they want to see. Okay. And on Blackboard, there's a handout that I submitted, or that I linked to you guys, and that handout shows the acronyms. It's basically this same acronym here, and this is the acronym I've used every year. But concerning the time that we're in, I want to say, don't panic. But for the lesson that we're covering right now, we're using the acronym PANIC. So it's kind of an irony, right? So let's look at what the letters stand for. So P stands for stating the parameters. What are we interested in? What is the problem asking us to find, to determine? And that's what we're going to do at the beginning, determine the parameter. A stands for assumptions. There's some assumptions that we have to check for when we're discussing this. And so in actuality, let me pull up the assumptions. So let me make sure I'm getting to it. Give me a moment. So assumptions. Here we go. And let me put it on a separate slide. Okay. So that's for step A. And then N, naming your interval, making sure you use the right name, because we could either be dealing with means or proportions, so I want to make sure that you're choosing the right one. Letter I is, find the interval. This is the calculation part. This is based on this formula that I showed you a little while ago. And then C, we're going to make a conclusionary statement. And I know it seems like a lot of steps, but once I show you an example or two, I think you'll get it. And I made sure to provide some examples on the slides. So this is the page that I was talking to you about on Blackboard. So we have the acronyms up here. Right now we're focusing on confidence intervals. This is the acronym here. Now the assumptions that we're talking about, I put the assumptions at the bottom. Okay. And there's 3 assumptions. One is a set for the means, one is for the proportions. And if we remember from sampling distributions, we dealt with either means or proportions. So in the same idea, there's assumptions for different samples, depending on if we're sampling for an average or for a proportion. So since we're working with means, these are the 3 assumptions we have to check for. Number 1, was there a random sample of the population? Number 2 is called the 10% condition. And on Blackboard, I put a link about explaining the 10% condition from Khan Academy. And then number 3 is n greater than 30. If you remember this is the central limit theorem. And so that makes sure that the data is normal. The population is normal. Okay. Let's look at the first example. Again, I gave you guys a handout, and this is the first example on the handout. And it says, oxides of nitrogen, called NOx for short, emitted by cars and trucks. Emitted by cars and trucks. So that's what I meant to put there. Are important contributors to air pollution. The amount of NOx emitted by a particular model varies from vehicle to vehicle. For one light truck model, NOx emissions vary with unknown mean and standard deviation of 0.4. So notice that it says an unknown mean, because we're going to use confidence intervals to estimate this mean. But they did happen to give us a standard deviation, which is nice. A standard deviation of 0.4 grams per mile. You test a simple random sample of 50 of these trucks. So our sample size is 50. Okay, our sample size, this is our n, is 50. And find the sample mean NOx level to be 8. So this 8 is my x bar. Give a 90% confidence interval for the mean NOx level. Okay, give a 90% confidence interval for the mean NOx level. So remember, if it says 90%, the percentage change given the problem, and this one's asking for 90%. Remember, 90% corresponds to the z value. Okay, and I'll talk more about that when we get to step I of the problem. But for now, let's look at step P. Okay. Step P for panic, right? P is saying state the parameter. What are we interested in the problem? We're interested in to estimate the true mean NOx level. The true mean NOx level, the oxides of nitrogen from the trucks, how much they emit, right? We're looking for the true average. But again, we're working with sample data and we're trying to estimate the true parameter. Okay, so that's step 1. Make sure you list what it is. And then in part A, we're going to do a checklist. Okay, so as you're working on the problems, make sure to put P, and then next to P, put the parameter that we're looking for with the symbol that corresponds to that parameter. In this case, the symbol for mean. And then acronym A, right? Write the 3 assumptions that's on that page that I showed you. So the first question is, was the sample random? Was the given sample random? And so what I'm going to do is I'm going to take that document and import it. Okay, and so if I look at the document, the handout that I gave you guys, does it say that the sample was random? And here it is. It says simple random sample of 50. Okay, so I'm going to say, number 1, it's given in the problem. Second question, was the sample size larger than 30? Was the sample size larger than 30? Well, yeah, right after it said that it was random, it said that the sample size was 50, n was 50. So yeah, for sure, the sample size is larger than 30. And again, what do we say? If the sample size is larger than 30, then it's normal. Okay. Next, third thing, 10% condition. And for this, we're going to make kind of a template statement and say, it's safe to infer the population is at least 500 trucks to ensure independence. Now, where the 500 comes from, let me show you where it comes from. This 500 came from multiplying the sample size times 10. So 10 times n. And what was n in the problem? What was the size of the sample? 50, right? So 50 times 10 is 500. It's 500. So it's safe to infer that the population is at least 500 to ensure independence. And so we want to make sure that our sample was independent. How do we do this? We want to make sure that the sample size that we took, the 50, is no more than 10% of all trucks on the road. Okay. Now again, I provided you guys a video on the 10% condition on Khan Academy, and I also recommend that you watch that one. For now, we've continued. We've done P and we've done A. Let's go to step N. We're actually going to use the same P, the same A. The only thing that's going to change is, so continuing here, step N, the name of the interval that we're looking for is a 90% confidence interval. So that's what I want you guys to write. For N, we're going to write a 90% confidence interval. Okay, and remember I said, 90% corresponds to a particular z-score. Now, if we look at our table from the last lesson, the normal table, and let me pull up that table right now. Let me put it as a separate slide. Okay, so is 90%, but we're going to look at it in a different way. Okay, so remember the normal curve. And if we're looking for 90%, it's going to be 90% centrally located. So I'm looking for the middle 90%. So if this is 90%, right, how much is on the tails? How much is here and here? You would say, there's 90 minus 100, or 100 minus 90 is 10. So that means that there's 5% here and 5% here. Okay. So in actuality, what we're looking for is not 90%. We're looking for the percent of the tail. Okay. The percent of the tail. So what's the percent of this tail? 5%. So when I'm going, we're looking for a 90% confidence interval, which is this blue area. But remember, the normal chart only looks at the tail parts. So if I have 90% in the middle, that means I have 5% on my left, 5% on my right. So if I look for 5%, that's going to give me the z value, and I looked at the table and I got a z value of 1.65. Okay, so now step I, the calculation part. What was our sample mean from the problem? The average NOx level was 8 grams. You remember if you look at the handout. Then we got a z-score of 1.645, and then the standard deviation is 0.4 divided by the square root of 50, because we sampled 50 trucks. So calculate this. The margin of error, if I calculate it here, it's 0.093, and then I'm going to add it and subtract it from 8. And so I have a lower bound and an upper bound. A lower bound and an upper bound. This is my interval. So my conclusionary statement is the following. We are 90% confident that the true mean Knox level, the parameter that we were interested in the beginning, lies between 7.907, which is my lower bound, and 8.9093, my upper bound, grams per mile. And we're done. That's it. All right. Number one has part A and part B. So the nice thing is, for part A and part B, we would have to do panic again for part B, but we're talking about the same problem. So for part B, part A was asking for a 90% confidence interval. Okay, 90% confidence interval. And so what was our tail here, right? If 90% is in the middle, then we have 5 and 5. And so when we look in our table at 5%, we find a z-value. It's going to be negative, right? But again, what are we doing here? We're doing plus and minus. So we use 5%, and we got an upper bound and a lower bound. Now in part B, what changed? If you remember this table that we saw in the last lesson, what I'm looking for is 90%, but I'm looking for it in the table. Is it going to be on the left side or the right side? Correct, it's going to be on the right side. And I'm looking for, I'm looking for 90%. I'm looking for 90%. So where do you guys see it? Do you guys see it somewhere? And the answer is no. In actuality, what we're going to be looking for, to my table, I'm actually going to look for 5%. 0.05. 0.05. Okay, so where is 0.05? I'm scanning. It's between these two. Let me move a little bit down. Okay. 1.6. Yeah, it's between these two. And I think we chose 1.6. Let me see. We chose 1.645. Okay, so that's using the calculator, but we're using the table. So I'm going to say 1.65. 1.65. And let me draw it out. So we're choosing 1.65. That's the closest one to 5%. Again, how did we get 5%? Part B. But how do you convert that into a decimal? 0.025. 0.025. So where is 0.025? That's there. What's the z-score that corresponds to 0.025? What is that? What is that value? It's 1.96. 1.96. Part A. What was our z-value for 0.025? It was 1.96. 1.96. Okay. Awesome. Let me go to it. We're looking for, in part B, if you read it on the handout, it says we're looking for a 95% interval. A 95% interval. So we're going to think about the normal diagram again. But this time, we're going a little bit wider. We're looking for 95% in the middle. So that makes our blue area wider. So how much is left on the tails? What's 100 minus 95? That's 5%. 5 divided by 2, 2.5%. 2.5%. Okay, so what do you think we're going to look for in the table? That's right, 2.5%. Okay. So what z-value are we going to use? 1.96. But do we have the same mean? Yes, right, because it's the same scenario, just different interval, different percentage. Same standard deviation? Yes. Same sample size? Yes. What's different is the 1.96. And so we calculate this margin of error, which is after the plus and the minus. We calculate it and we get 0.111. And so we're going to add and subtract to get my lower and my upper bound. And now I'm making a second conclusionary statement because I'm doing part B, right? We are 95% confident that the true mean NOx level lies between 7.889 and 8.111 grams per mile. So let me go between the two slides just to compare them, right? So let me go back to part A. Ready? 90 changed to 95%. 90% changed to 95%. So then what's on my tails? 2.5 and 2.5. So that's the percentage that I'm going to be looking for in the table, which leads me to the z-value, and I get a lower bound and an upper bound. Okay? Okay, so let's do one more example. And then let's do number 4. Number 4. The Financial Aid Office wishes to estimate the mean cost of textbooks per quarter for students at a particular university. For the estimate to be useful, it should be within $20 of the true mean. Okay, it should be within $20 of the true mean. To determine the required sample size, we must have a value for sigma, the standard deviation. The Financial Aid Office is pretty sure that the amount spent on textbooks varies widely, with most values between 50 and 45. Between 50 and 45. Okay. So it's saying if my standard deviation is 100, how large of a sample should be used to be 95% confident of achieving this level of accuracy? Okay. So a couple of things you have to keep in mind is, let me use a different color here, is they're wondering about the sample size. That's the question, right? How large of a sample should be used? And notice they gave us a couple of things. They gave us the standard deviation is 100. And something that they gave us, but maybe we didn't think of it, is it says that for the estimate to be useful, it should be within $20 of the true mean. $20, within $20 of the true mean. So what this is, it means that the margin of error is $20. The margin of error is $20. Okay? So how is this important, right? Remember what I said in the beginning, or I think it was the second slide, or first. So the estimate plus or minus the margin of error and so what we're going to use actually is just this part. Okay, but remember our formula, right? It was x bar plus or minus, sorry, write it a little bit nicer, plus or minus the z-score times the standard deviation over the square root of n, right? So what does that mean? Well, this means that, this part of the formula is the margin of error. So everything that I boxed in red is the margin of error. Okay, so I'm going to make an equality. Can I make an equality? We want to construct a 95% confidence interval. 95% confidence interval. Question: how large of a sample should be used to be 95% confident in achieving this level of accuracy? Yeah, I'm going to say the margin of error is equal to the z-value times the standard deviation over the square root of n. But didn't they give us n? Or no, n is what we're looking for, right? Did they give us a standard deviation? Yes, right? Did they give us a margin of error? Yes, that was 20. So I have the margin of error, check, right? I have the standard deviation, I don't have the sample size. So how do I find z? Well, remember they said that we want to construct, let me go. %95 confidence interval. So remember, if I'm thinking about, sorry, I'm going to draw this a little bit better. If I'm thinking about normal model, and I'm thinking about 95%, then I'm thinking about this being 95%, right? How much is on the tails here? What's 100 minus 95? 5%, but divided by 2 pieces, that's 2.5%. And on the other side, it's what? 2.5%. And so we're going to convert this to a decimal and look for it on the table. And just to reiterate here, 2.5% is equal to 0.025. 2.5% is 0.025. And remember when we went to do we have the z-value? Yeah, we do. The z-value is 1.96. Okay, so we have everything we need. Let me plug in everything I have in blue. What's my margin of error? It's $20, right? What's my z-value that I found in the table? It's 1.96. What's the standard deviation? That's 100 over the square root of n. So So I got to solve for n. Okay. So a couple of things I can do. Can I multiply the 100 times 1.96? Yeah, that's 196 over the square root of n. And then I can multiply both sides times the square root of n. So that, let me get a different color here. So that these cancel. Okay. And then, no, group them. And, sorry, I did something here. And then we're going to say, we're going to write 20 times the square root of n equals 196. And then we're going to divide both sides by 20. And that's going to give us 9.8, I believe. How do you get rid of a square root? Right, you square both sides. Then we get n equals 96.04. And so we would round up and say we need a sample size of at least 97 books. To explain where everything's coming from, and what the question was, right? The question was, how large of a sample? And so we got a sample size of 96. So at the very least, right, our margin of error has to be within $20. So that means that at the very least we need 96. So we need 96 or more. So I'm just going to say, 97. So we need a sample size of at least 97 textbooks. All right, so I want to thank you. For joining me today. And I hope this explains the PowerPoint a little bit better. If you have any questions, feel free to email me. Make sure you're keeping up to date on whatever I post on Blackboard. If you have any clarifications or concerns or anything, feel free to email me. And again, stay safe and just take care of yourself and those around you. And have a great rest of your day. Thank you. This is what this last slide does. It does the math, but I at least wanted